Today we are going to study about density of states for a two-dimensional material. So first of all, we need to know what is a two-dimensional material. A two-dimensional material is a material in which the charge carriers are free to move in two directions while they are not free to move in one of the directions. So in this case, the charge carriers are free to move in Lx and Ly direction while they feel confinement in Lz direction. So what does confinement mean? It means that the length of that direction should be, of that structure, should be of the order of de Broglie wavelength, so that the electron, when it is moving in that particular direction, feels confinement and its energy levels are quantized. So for such a structure, the dispersion relation is given by this. Where we have to use effective mass of an electron in place of a free electron, because the electron is moving in crystal structure while k is the wave vector. K wave vector here actually is composed of three components, which is kx, ky and kz. So in terms of its components, this equation turns out to be this. Now, because energy quantization will be taking place in one of the directions, let us say that because in this direction it is Lz direction, we already know that only certain wavelengths will be allowed in that direction because of the confinement effect, and because of that, Kz will have some discrete values and Kx and Ky will have continuous values. So the energy spectrum in the state in this case consists of overlapping subbands with the parabolic dispersion relation. So you see, this is a parabolic dispersion relation in x and y direction, while it will be discrete in the z direction. So if we compare it with bulk, we see that in bulk we have one band, and for each value of k you will have a value of energy, and all the k values will be allowed. While for a two-dimensional material, you see that instead of one band, you will have many subbands, and these subbands will be in such a manner that the minima of these subbands will be such that kx and ky will be, when it will be 0, then you will get E equal to this. So this will give you the minimum value of energy. So by that we can find out what will be the minimum value of energy for the first subband, and it will be E1. So we'll put the value 1 here, so it will be h bar square pi square upon 2m star Lz square. Similarly, for the second subband also, the minimum energy will be given by n squared will be 2 squared into h bar squared pi squared upon Lz squared, and so on. So for the minimum energy of the nth subband will be given by En is equal to n square of the first minimum energy of the first subband. And the radius of, so if you see this parabola, actually it is a parabola in two directions. So it will be a cone kind of a structure, not necessarily exactly cone, but it will have a circular, from above it will be like a circle. The area will be like a circle. And the radius of this area will be kx square plus ky square under root. So in k-space, if we draw in the k-space, we know that in bulk all the k values will be allowed. So and it will be continuous energy values, while equal energy surface on this k diagram will be a sphere, which will be, and the maximum value of this surface will be given by in fact, if we draw multiple surfaces here, they will all have a radius of this, and the maximum value of k will be correspond to the maximum value of energy that is permitted in that particular structure. So because it is a sphere, it will have a radius of kx square plus ky square plus kz square in case of bulk. But in case of a two-dimensional material, you see that k will have continuous energy, will have continuous values in x and y direction, while it will have discrete values in the z direction. So we can have all the values will be permitted in kx and ky, but only a few values will be permitted in the kz direction, which leads to very important and interesting results. So let us say that now we are drawing this vector k vector here, which is in such a manner that it will have two components, kx component and ky component. So for one kx, ky and kz, you will have one point over here. Similarly, you can draw another k vector which will have a kx component and a ky component and a kz component. But it has to be taken care that the kz component will always stay the same. And this we are talking about the first subband. This will also be true for the second subband. So it means that any k vector that we draw in this space will be in such a manner that its z component will have to come here. There will be no k vector allowed between this first kz vector and the second kz vector. So if we have this k vector, it will have one component here and two components in this direction. So if we draw many k vectors like this, such that their kz is constant, it will actually turn out to be a surface. And in this surface, equal energy surface will be a circle. So this actually surface will be a circle for equal energy, and the maximum radius of the circle will depend upon the maximum permitted energy of that particular material. And because it is in kx ky plane, the area occupied by one state will be given by pi upon lx into pi upon ly, because we are talking about the k space. So in the k space, the distance between two k points is given by pi upon l. But here, because we have two directions, so it will pi upon lx upon pi upon ly. If lx and ly are same, then it will be pi upon l squared. So for clarity's sake, I have drawn it here. Now this k vector will be the maximum k that is allowed for the maximum energy that is permitted in that particular material. So if we know the number of states in this area and divide it by the area occupied by one state, then that will give you the number of states possible or number of energy levels that will be possible, because for each value of k there will be a corresponding energy level. So if we know the number of k vectors or number of k states possible, we can also know the number of energy states that will be possible. So the total area of this circle will be pi k square, and area occupied by one state will be pi upon lx into pi upon ly. But if lx is equal to ly, then it will be pi upon l squared. We'll also have to use multiply it with 1 upon 4, 1/4, because k cannot have negative values. So only the positive values we will have to consider. And we'll also have to multiply it with 2, because the number of states will be double of the states that we are talking about here, because each electron can have 2 spin states. So this number of states for the first subband turns out to be k square l square upon 2 pi. So from the dispersion relation, we can find out the value of k square, and we can put it in this equation, and we can find out a number of states in terms of energy. So the number of states in terms of energy, it depends upon E minus E1. E minus EC minus E1. So in order to find the density of states, because we know the density of states will be given by 1 upon the area in the real space. Now this area will be perpendicular to the axis of quantization or axis of confinement. So in this case, it will be 1 upon Lx into Ly, and the derivative of the number of states with respect to energy. So it will, if we take a derivative of this function, because EC and E1 are constant, we'll have to take derivative with respect to E, and so it will turn out to be m star upon pi h bar squared. So the density of state comes out to be this. Now it has to be emphasized here that the number of states depends linearly on energy, while the density of states is independent of energy. And this we are talking about the first subband. So it means that in the first subband, what will happen is that the density of state will stay constant as we move from the lowest value of energy to the highest permissible value of energy in the first subband. Now how is it this possible? Because we know that the states that we are calculating are actually on these circles that I have drawn here, and because at lower, when the smaller the circle, larger the number of states, and the larger the diameter of the circle, lesser the number of states. That is why the density will stay constant. Now we know that the number of states depends linearly on energy. So for the second subband, it will be number of states in the first subband plus the number of states in the second subband. So the number of states turn out to be this. And if we take a derivative of it and multiply it with 1 upon L squared, then we'll get the density of states in the second subband. So we find out that the density of states in the second subband will actually be twice the density of states in the first subband. And the number of states will also be twice the number of states that were permitted in the first subband, and some extra terms also are there. Similarly, for the third subband, we found that the density of states will be 3 times the density of states of the first subband. Similarly, we can calculate it for n subbands, and we see that the number of density of states will be n times the density of states of the first subband. So what does it mean? If we draw the density of state versus energy, so for bulk we know that the density of state increases and then it saturates. But the density of states for two-dimensional material, if below E1 there is no density of states, so it will be 0. And then at E1 there is a sharp increase in density of states. And then it stays constant when we move from E1 to E2. And then again there is a sharp increase by m star upon pi h bar squared, and then again it is constant. So what it means is, if we draw the EK diagram horizontally, we see that there will be no density of states below E1, while as we move from E1 to E2, the density of states will stay constant. And again it will be then, when it will reach here, it will double, and then it will stay double from here to here. And that is why, and this is what is meant by constant density of state in a two-dimensional material. It can also be seen that the number of states actually depends linearly on energy. So as we move from E1 to E2, it will increase, and it will keep on increasing linearly as we move from one subband to the other. Also, if Lz, the confinement direction, the length of that direction increases, then the difference between E2 and E1 will decrease, and these subbands actually will collapse into one band, and that will be then it will behave like a bulk material.